You know, I had a bit of a weird moment yesterday. I was walking downtown, right past that massive new mixed-use tower they're putting up.
Oh, the one with the cantilevered edge?
That's the one. It looks like it's defying gravity. And everyone else on the street, they're all looking up, craning their necks at the glass and the steel. But I found myself just staring at the mud.
Staring at the mud. That is usually a symptom of reading too many geotechnical engineering textbooks, or maybe a midlife crisis.
Definitely the textbooks. I've been deep in the chapters we're covering today, site exploration and shallow foundations, and it completely rewired how I look at a city. We obsess over the skyline, the aesthetics.
The part you can see.
Exactly. But the sources make this incredibly profound point right out of the gate. A structure is only as strong as its negotiation with the ground.
That is the perfect word for it, a negotiation. We tend to think of buildings as these, static, conquered things. We built it, it stays there. But the ground is alive. In a way, it's chaotic, it's historical, and it's stubborn. And if you don't listen to what the dirt is telling you during that negotiation, the dirt wins.
And when the dirt wins.
Buildings fall down.
So that is our mission for this deep dive. We are looking down. We're going to unpack the detective work of figuring out what the Earth is actually made of, which is way more complex than I thought, and then get into the physics, the heavy math that ensures a million-pound skyscraper doesn't just, slip into the abyss.
We're going to cover the CSI phase, investigating the crime scene before the crime happens.
I like that.
Then the battle of the stress tests, and finally, the formulas that keep us all safe.
So let's start with that detective work. The technical term is site exploration, but honestly, it reads like a police procedural. I think the assumption most people have, I certainly did, is that you just drive a big drill rig onto a lot and start punching holes.
And if you do that, you are going to lose a lot of money. And you might lose a drill rig in a swamp you didn't know was there. No, the investigation starts way before you ever touch the dirt. It starts with the paper trail.
The preliminary phase. This is the armchair detective part.
Exactly. You're playing historian. You're pulling geological maps, aerial photos from the 1950s, old mining reports. You have to know, was this site a swamp in 1920 that got filled in with trash?
Right.
Was there a chemical factory here that leaked solvents into the clay? If you don't know the history, the soil will surprise you. And in construction, surprises are always expensive.
The sources also mention field reconnaissance. This isn't just driving by, it's getting out and walking the beat. And what struck me is that you aren't just looking at your own site, you're spying on the neighbors.
Oh, the neighbors tell you everything. If the building next door has cracks in the masonry, or if the door frames are skewed, that is a massive red flag. It tells you the soil is shifting or settling.
So you're looking for clues everywhere.
Everywhere. You're also looking for vegetation. Are there reeds growing in the corner? That probably means high groundwater. Is the ground undulating? Maybe there was a landslide a century ago. You're reading the landscape.
Okay, so you've done the history, you've walked the beat, you've profiled the neighborhood. Now it's time for the main event, subsurface exploration.
This is where we bring in the boreholes. It is the gold standard. We drill into the earth to see the stratigraphy, the layer cake of the soil. You need to know where the sand ends and the clay begins.
I found the math on how deep you drill to be surprisingly specific. It's not just drill until it feels solid. There's an actual formula.
There is. And it's all about stress. See, when you put a heavy building on the ground, that weight doesn't just sit on the surface. It radiates downward, spreading out deeper and wider. It creates what we call a bulb of pressure deep underground.
And you have to investigate that entire bulb.
You have to go deep enough to cover it.
The rule of thumb in the text was 6s to the power of 0.7 plus d.
Right. And let's break that down. S is the number of stories. D is the depth of the foundation. But look at that exponent on the stories. 0.7.
Yeah, I noticed that. It's not linear. It's not just 10 feet for every story.
Exactly right. A 50-story building doesn't generate a pressure bulb 5 times deeper than a 10-story building. The stress dissipates. But the formula ensures that for a massive tower, you are going way down, sometimes 50, 60, 100 meters, to make sure there isn't a secret layer of soft mush waiting to collapse.
But while we're down there, we're grabbing samples. But the sources make this huge distinction between disturbed and undisturbed samples. And I feel like this is the difference between a crime scene photo and a crime scene smoothie.
That's a vivid image, but yes.
Yeah.
Let's use a baking analogy. Imagine you want to test the structural integrity of a delicate chocolate souffle.
Okay, I'm with you.
If I take a split spoon sampler, which is basically a thick-walled metal tube, and I hammer it into the souffle, what happens?
Total destruction.
Right. I pull it out, and I have a handful of chocolate and egg. I know the ingredients. I can tell you it's chocolate. But the structure, the air pockets, it's smashed. That's the disturbed sample.
So you use that for just identification. Is it sand? Is it clay?
Exactly. But I can't test how strong it is because I've already broken it.
So for the undisturbed sample, we need the Shelby tube.
The Shelby tube is like a very sharp, thin cookie cutter. We don't hammer it. We push it hydraulically with one smooth, slow motion into soft soil. It slices a cylinder of earth without crushing the internal skeleton of the soil particles.
So when you get that to the lab, it's basically pristine.
As close as we can get, and there's a metric for this, the area ratio. It measures how thick the walls of your tube are compared to the sample. If the metal is too thick, if it displaces more than 10% of the volume, it's garbage. It's disturbed.
So you need that ratio under 10%.
You have to.
Okay, so we've got our samples heading to the lab, but we also do testing right there in the field. And this seems like a bit of a rivalry, the battle of the tests. In one corner, we have the old veteran, the SPT.
The standard penetration test. This is the grandfather of geotech. It's been around since the 1920s. It's crude, it's loud, it's violent, but everyone uses it because it's robust.
Walk us through it. It sounds intense.
It is. You have a 63.5 kilogram hammer, about 140 pounds. You lift it up exactly 0.76 meters, and you drop it onto the drill rod, bang.
And you're just counting the bangs.
You're counting the blows. How many times do I have to drop this hammer to drive the sampler 12 inches or 300 millimeters into the ground? That number is the N value.
So high N value means hard ground, low N value, soft ground. Simple enough.
In theory, yes. If I drop the hammer 50 times and it barely moves, that's dense soil. If I drop it twice and it sinks a foot, that's loose. It's an index of strength.
But I sense a massive but coming. The sources were throwing up a lot of caution tape around the SPT. It seems like it has some trust issues.
Huge trust issues. Because the test is just so messy. I mean, think about the variables. Is the hammer rusty? Is the rope loose? Is the borehole dirty? And critically, how much energy is actually getting to the sampler?
The efficiency problem.
Right. An old manual hammer might only deliver 45% of the energy because of friction in the pulley. A new automatic trip hammer might deliver 80%. An N value of 20 from one rig might mean something totally different than an N value of 20 from another rig.
So you have to fix the math to compare apples to apples.
We normalize everything. We use correction factors to convert every reading to N60, what the number would be if the hammer was exactly 60% efficient. If you don't do that, your data is just garbage. And the sources are adamant. Never rely on SPT for clay strength. It's just too unreliable.
So if the SPT is the blunt instrument, the alternative is the CPT, the cone penetration test. This feels like the digital upgrade.
It is. No hammers, no banging. A truck pushes an electronic cone steadily into the ground, and it has sensors on the tip and along the side measuring resistance and friction.
And the key difference is the data stream, right?
Yeah.
The SPT gives you a number every, meter or so? The CPT is continuous.
That's the game changer. Imagine reading a mystery novel, but you only get to read one word on every page. That's the SPT. You might miss the clue.
You'd miss the whole plot.
Exactly. The CPT reads every single word. If there's a 3-inch layer of slime, a weak lens, sandwiched between two strong layers, the SPT will jump right over it. The CBC will see it.
And that thin layer of slime could be the very thing that brings the building down.
It could be. That's why CPT is becoming the favorite for critical projects. It sees the hidden weaknesses.
Okay, so we have drilled, we have hammered, we have probed, we have a picture of the underground, and now we have to make a decision. We need to build a foundation, and specifically, we are looking at shallow foundations.
Right. Shallow foundations are kind of the economy option. If the topsoil is strong enough, we don't need to drive expensive piles down to bedrock. We could just sit the building on the surface.
We're talking spread footings, those concrete pads under columns, or mat foundations, which are basically giant concrete rafts under the whole building.
Yep.
But when designing these, the sources mention the 2 commandments you have to follow,
Yep.
ULS and SLS.
Ultimate limit state and serviceability limit state. These are the 2 ways a foundation can fail.
Okay, break those down for us. What's the difference?
ULS is about catastrophe. It answers the question, will the soil break? If you violate ULS, the soil shears, the foundation punches through the earth, and the building collapses.
That's the don't kill anyone rule.
Pretty much.
Hmm.
And SLS is about performance. It answers, will the building still work? The building might not fall down, but if it sinks 10 inches, the pipes will burst. If it tilts, the elevator doors won't open.
So the building becomes a giant, useless sculpture.
Exactly. That is an SLS failure. And interestingly, SLS is often the stricter one. You usually hit your settlement limit long before you hit the total collapse limit.
Right, so to avoid that collapse, we have to calculate the bearing capacity. This is where we get into the heavy weights of soil mechanics. Terzaghi versus Vasic.
This is the core of the discipline. Carl Terzaghi. He is the undisputed father of soil mechanics. In the 1940s, he came up with the equation that changed everything.
And his formula is built on 3 pillars, the 3 components of strength. I want to walk through these because they really explain how soil holds up a building.
Let's do it.
First term, cohesion.
Think of this as the glue term. If you're building on clay, the particles stick together chemically. That electrical stickiness resists the weight of the building trying to push them apart.
Okay, so that's the glue. Second term, surcharge. This one was a bit counterintuitive to me.
This is the clamp term. It represents the weight of the soil next to the footing. Imagine you're trying to push a block of wood into the sand. If I pile heavy sandbags on the surface right next to where you're pushing, it's harder for you to push the block down right.
Because the soil underneath has nowhere to escape to.
Exactly. You are clamping the failure zone shut. That's why deeper foundations are stronger. You have more soil pushing down on the sides.
And the third term, friction and weight.
This is the grit term. It accounts for the friction of the soil wedge directly underneath the footing. Soil strength relies heavily on particles rubbing against each other.
So glue plus clamp plus grit equals bearing capacity.
In Terzaghi's world, yes. But Terzaghi lived in a simplified world. He assumed the footing was a long, continuous string.
Like under a wall.
Right. He assumed the load was perfectly vertical. He assumed the ground was flat.
But in the real world, footings are squares. Buildings have wind pushing them sideways. We build on hills.
And that is why we need Vesic. In the 1970s, Vesic took Terzaghi's formula and patched it for reality. We called the alphabet soup formula.
Because he added a factor for literally everything.
Everything. Terzaghi assumes a strip. Vesic adds a sheep factor because the square footing is actually stronger than a strip. It confines the soil better in 3D.
Terzaghi assumes a vertical load.
Vesic adds an inclination factor. If the wind is blowing your skyscraper, the load comes in at an angle. That angle slashes your bearing capacity because it introduces horizontal shear. Vesic accounts for that.
And he adds depth factors, ground slope factors. Basically, Vesic is the tool you actually use when things get messy.
Terzaghi is the concept. Vesic is the application.
Speaking of things getting messy, let's talk about the disruptors, the things that try to break the math. And the biggest villain in geotechnical engineering by far is water.
Water changes everything. It is the enemy.
The reading talks about the effective unit weight. Explain this to me. Why does water make soil so weak?
Think about lifting a heavy rock underwater. It feels lighter, right?
Yeah, buoyancy.
Well, soil particles are buoyant too. When the water table rises and submerges the soil, the particles effectively lose weight. Now remember the grit term, the friction. It depends on how hard particles are pressing against each other.
So if the water lifts them up?
They don't press as hard, the friction drops, the strength drops. If the water table rises all the way to the surface, your bearing capacity can get cut in half, literally 50%.
That is terrifying. So you design a building in the dry season, everything looks great. Then the rainy season hits, the water table comes up, and your safety margin is gone.
If you didn't account for it, yes. That's why we always design for the highest anticipated groundwater level. You have to assume the worst case scenario.
Wow. Okay, disruptor number 2, eccentric loading. This sounds like a psychological condition.
It does, doesn't it? It's actually about where the column sits on the footing. Ideally, it's right in the middle. The pressure is uniform, like standing flat on both feet.
But sometimes architects want the column on the edge.
Or a bending moment twists the column. Now you're leaning. And the pressure distribution changes from a nice rectangle to a trapezoid. You're pressing hard on one side and lifting off on the other.
This leads to this geometric concept called the kern. It sounds mystical. Stay within the kern.
It's just a diamond shape in the center of the footing. The rule is simple. If your load resultant stays inside that diamond, if the eccentricity is less than 1/6 of the width, you're fine. The whole footing stays on the ground.
But if you go outside the kern,
Then you have liftoff. The heel of the footing actually lifts off the soil.
which means tension, And soil cannot take tension.
Not exactly. You can't pull dirt. It
Yeah.
just separates. So that part of the footing is doing absolutely nothing. It's useless.
So how do engineers fix this? The math trick here was wild to me, the effective width method.
It is a clever hack. If part of the footing is listing off, we just pretend it doesn't exist. We calculate a new, smaller width. We say, okay, the footing is actually only this wide.
You essentially fire the part of the foundation that isn't doing its job.
Exactly. We reduce the dimensions in the formula and check if the remaining smaller area is strong enough. It's better to assume a smaller footing than to trust a part of it that's floating in the air.
Final disruptor, layered soils. We touched on this with the CPT. What happens if you have a strong layer of sand on top of a weak layer of clay?
This is the classic trap. You run a shallow test, you see strong sand, and you think, great, high bearing capacity. But that stress bulb we talked about, it goes deep. It punches right through that sand crust and hits the clay.
So the sand might hold, but the clay underneath just squishes.
It's called punching shear. To solve it, you can't just use the properties of the sand. You have to create a composite model. You do a weighted average of the cohesion and friction for all the layers within that failure zone. You create a mathematical Frankenstein soil to get a realistic number.
So we've accounted for the layers, the water, the leaning loads. We run the Vesage formula, we get a number. The soil can hold, say, 500 kilopascals. Do we load it to 500?
Absolutely not.
I knew you were going to say that.
We load it to maybe 150 or 200. This brings us to the most important number in engineering, the factor of safety.
Usually 2 to 3 for foundations. That means we build it to be 2 or 3 times stronger than the math says it needs to be.
Yes, and I want to be clear why. It's not because we are bad at math. It's because soil is not steel. Steel's made in a factory. We know exactly how it behaves. Soil is made by nature. It has wormholes, ancient root paths, soft pockets we missed between boreholes.
So the factor of safety is basically an apology to nature.
It's an admission of humility. It's us saying, we've drilled and tested and calculated, but we know the earth still has secrets.
That is a really humbling thought to end on. We do all this high-tech CSI work, all this calculus, just to build a buffer against the unknown.
And that buffer is what lets us sleep at night.
So here is a final thought for everyone listening. Next time you are in the city, don't just look up at the steel and glass. Look down. Think about that invisible bulb of pressure radiating into the dark, chaotic earth beneath your feet. Think about the negotiation happening right there, keeping you suspended above the mud.
And hope the engineers check the water table.
Exactly. Thanks for listening to The Deep Dive.
Stay curious.